Okay, can you see the screen?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay. So this was what we just saw was discontinuous conduction. Okay. If you go on, if you increase the inductance, or if you decrease the firing angle, or you increase the magnitude of current, then it is possible that your angle beta will go on increasing. Okay. And if the value of beta becomes equal to or greater than pi plus alpha, then what you get is continuous conduction. Because before the load current can become zero, the next set of SCRs are triggered so that the load current again starts increasing. Correct?
Yes, sir.
So the boundary between discontinuous and continuous conduction is obtained when beta is equal to pi plus alpha. Okay. So if you substitute beta is equal to pi plus alpha, if you substitute beta is equal to pi plus alpha in the equation for current and you solve it. Okay, once again, I'm not writing the formulae. Okay, this derivation I'm not writing because that will take a lot of time on the this keyboard, this board. Okay, so I'm directly writing the final result. Okay, what is this? Omega is speed.
Speed, sir.
And the C there is for critical. Okay, this is the critical speed. So the critical speed is given by RAVM by ZK sine alpha minus phi divided by 1 plus e to the power minus pi quad phi divided by e to the power minus pi quad phi minus 1. Okay, so this critical speed, this separates continuous and discontinuous conduction for a given value of alpha. Okay, for a given value of alpha. Means if you're okay, of course, once your motor is constructed, your armature inductance is constant. You cannot increase or decrease it. And if your load is also assumed to be constant, then the only variable here is alpha. So depending on the value of alpha, as I told you about the three factors, depending on the value of alpha, your continuous or discontinuous conduction will be decided or can be found out by using this expression for a critical speed. Okay. So suppose the critical speed is, let us say, 1000 RPM. Okay. I'm converting it into RPM instead of radian per second. Okay. Suppose the critical speed is 1000 RPM and the actual speed is 1150 RPM. So tell me whether you will get continuous or discontinuous conduction. Is everyone clear what is critical speed? Sumit?
Yes, sir. When you discontinuous conduction.
It is the speed, it is the boundary between continuous
Yes,
and
sir.
discontinuous conduction
Discontinuous one.
for a
Yes, sir.
given value of alpha.
Yes,
So
sir.
suppose the critical speed is 1000 RPM and the actual speed is 1150 RPM. Will you get continuous conduction or discontinuous conduction?
Discontinuous conduction.
Anybody saying continuous? Nobody? Okay, why discontinuous? Subhajit?
I'm sir thinking about that the logic, sir. I
ठीक
don't.
है. Anyone else?
Sir, omega proportional to back EMF, sir.
Hmm. Yes.
So, sir, if omega increases, back EMF will also increase and the
Hmm.
current will decrease, sir.
Correct. That is the right answer. ठीक है. Back EMF is proportional to the speed. So if your speed becomes greater than the critical speed, your back EMF becomes greater than the critical back EMF, so that your armature current will be less than the critical armature current, and hence your drive will operate in discontinuous conduction mode. Okay, clear to everyone?
Yes, sir. Yes,
Yes,
sir.
sir. Yes.
Okay, ठीक है. चलो. If your beta is equal to or greater than pi plus alpha, then what happens is your drive goes into continuous conduction mode. So in continuous conduction mode, before the load current can become zero, the other pair of thyristors are triggered. Okay. So what happens is, so what happens is you are triggering T1, T2 here. T1, T2 keep on conducting. Your armature voltage is equal to the supply voltage. And here, before the load current becomes zero, you trigger T3 and T4 so that your armature voltage becomes equal to the negative of supply voltage. And it remains equal to the negative of supply voltage till T3, T4 conduct. Once again, before the current can become zero, you turn on T1 and T2. Okay? So this is the armature voltage waveform if the conduction is continuous. The current waveform will be something like this. Okay, clear? Yes.
Yes, sir. Yes, sir.
So now there is no beta here, or beta is equal to pi plus alpha or greater than pi plus alpha. So in this case, you don't need the value of beta to find the armature voltage, average armature voltage, or DC component of the armature voltage. Okay. So the average armature voltage will simply be equal to 1 upon pi integral from alpha to pi plus alpha Vm sin omega t d omega t. Okay. Or it will be equal to 2 Vm by pi cos alpha. And I think you have seen this expression before.
Yes, sir.
Average output
Yes, sir.
voltage is equal to 2 Vm by pi cos alpha. But this expression is valid only if the conduction is continuous. Okay? Only if the conduction is continuous, not if it is discontinuous. And then if we substitute it in the expression for speed, omega m will be equal to 2 Vm by pi k cos alpha minus Ra by k squared into t. Okay? So that is the expression for speed. So as you can see, in the case of continuous conduction, the no load speed is a function of alpha. Okay? As you change the value of alpha, your no load speed will change. Okay? However, the slope is still same. Hmm? The slope is still same. So you won't get exactly, uh, means you will get parallel lines, but not at the time of starting. Okay? If we try to draw the speed torque characteristic, let us say this is without any control. Okay? Natural characteristic. Then this will be the nature of the स्पीड टॉर्क कैरेक्टरिस्टिक, ठीक है, something like this, ठीक है. These points will not be parallel, but after the line progresses it will be parallel. Okay, clear? Okay, so what are the problems with this converter, the converter that we have just seen? What are the different methods for armature voltage control? Can anyone tell me? One method you are seeing here. Apart from this, what are the other methods of controlling the armature voltage?
Resistance control.
No, resistance control.
Ward-Leonard method.
Yes, Ward Leonard method. है ना? What was the Ward Leonard method? Does anyone remember?
Sir, a motor and generator couple is used. Motor is used as prime mover and generator is used to generate the voltage. By controlling the motor speed, we can control the armature voltage. I mean generator voltage, and generator voltage is connected to the armature. Something like that.
ठीक है. So you have a three-phase supply which is connected to an induction motor, ठीक है, which runs at constant speed. Don't change the speed of that motor, ठीक है, because you are controlling speed of DC motor. For that you are using an induction motor. If you have to control the speed of induction motor also, then it is a very foolish method, you can say, ठीक है. That induction motor is run at constant speed and it drives the generator at constant speed. So how do you change the voltage of the generator?
So generator field control.
Generators a field. There is a tapping.
Yes, by changing the field current of the generator, you control the generator voltage, and that generator voltage is fed to the motor whose speed is to be controlled. Okay, so that was the Ward-Leonard method. Very good method. Okay, no harmonics, but some very big disadvantages, such as
The speed limit range, sir, is it's low, sir. That some
no, that was not the disadvantage.
Bulky size, sir.
Yes, to control one motor, you needed one more motor and one generator. Right? So the cost was too much and the space required also was very high. Okay? That was the disadvantage of Ward-Leonard method. But the advantage was you could get linear speed control over a wide range and there were no harmonics introduced into the supply. Okay? That was one method. Another method is you can use transformer with taps with an uncontrolled rectifier. The uncontrolled rectifier converts the AC into DC and the transformer is responsible for changing the voltage. So is that a good method? Yes.
under running condition. It is difficult to change the tap.
No, you have on-load tap changes.
So there will be spark in the taps during change because the current is high.
On-load tap changes are designed to handle that.
Sir, harmonics problem, sir.
Harmonics रहेगा, but it will be less than this. Okay? Because the firing angle is 0. Anything else? Transformer with taps and an uncontrolled rectifier.
So secondary side tap is very much hard to estimate where the tap will be located. I mean there will be magnetic saturation problem or something.
The tap will come with the tappings will come
Sir,
installed
smooth
to the
control will not
transformer.
be there, sir.
Yes, that is the answer. Not what all of you were saying. Those are not the answers. The answer is you get step control of speed. Okay? For example, if you have 5 taps, you can get only 5 or 6 speeds. Correct? But if you want smooth control or any value of speed, then that transformer with taps, it is not possible to obtain with that method. Okay. The third one is this. Okay. As compared to the Ward-Leonard method, it has a very small footprint. The cost is also less. As compared with the transformer thing, here you can get smooth control of speed. What are the drawbacks of this method?
So harmonics problem.
Where will be the harmonics, in the load or in the supply?
So in the supply side.
Yes, harmonics will be introduced into the supply side. Which harmonics? Which harmonics? Odd, even?
Odd harmonics.
Odd harmonics. If you are using a full wave rectifier. If you are using a half wave rectifier, then it will have even harmonics also, DC component also. Okay, that is why half wave rectifiers are never preferred unless your load is very small. Okay, so it has to be a full wave rectifier so that you only have odd harmonics. What about the power factor? What is the formula for power factor? Supply power factor.
Displacement factor into distortion factor.
Yes. So the supply power factor, that is equal to IS1 upon IS into cos phi. Okay. Where IS1 is the RMS value of fundamental component of the supply current. Okay. IS is the RMS value of the supply current, and phi is the angle between the supply voltage phi is the angle between the supply voltage and the fundamental component of supply current. Okay. Now, in case of the rectifier that we have just seen, this phi is equal to alpha. Okay. So that your supply power factor becomes equal to IS1 upon IS into cos alpha. Okay. If you assume that the inductance is so high that your output current is constant, then in that case, this IS1, I think, is 2 root 2 I0 upon pi. Okay. And IS will be equal to I0. So I0 will get cancelled. So supply power factor will become 2 root 2 upon pi into cos alpha. Okay. Only when the load current is constant. Okay. So this power factor is heavily dependent on the value of alpha. If alpha is equal to 90 degrees, your power factor becomes equal to, if alpha is equal to 90 degrees, your power factor becomes
0.
Okay. So as you go on increasing alpha from 0 to 90, your supply power factor goes on decreasing. Okay. How can you improve the power factor?
Sir, by increasing the number of pulses, we can reduce the harmonic. That is
You can.
by that.
Okay.
That lower order harmonic we can use.
Okay. Anyone else? How can you improve the power factor?
So using low pass filter.
Using low pass filter.
So cascaded connection.
Cascaded connection. Okay. Or anyone else? No one? One method of improving the power factor is to go for, yes,
Semi-converter.
yes, semi-converter or half controlled converter. Okay. So I'll not go into the working of the semi-converter. Okay. You have already studied that in power electronics. The working is more or less similar.
Sir, why it will improve the power factor, sir?
I'm coming to that. So when you turn on T1, positive half cycle, when you turn on T1, T1 and D1 will conduct. And as soon as the negative half cycle comes, D2 gets forward biased. So your current starts freewheeling through T1 and D2. Then in the negative half cycle, when you turn on T2, then T2 and D2 conduct. T2 and D2 conduct. And again, when the positive half cycle starts, D1 gets forward biased. So your current starts freewheeling through T2 and D1. Okay. So when T1 and D1 are conducting, current is flowing from the supply, correct? Supply current is positive and same as the output current. Whereas when T2 and D2 are conducting, current is again flowing from the supply, but it is negative of the output current. And when there is freewheeling, either through T1 D2 or T2 D1, the supply current is 0, correct?
Yes, sir.
So let us assume that the conduction is continuous and the inductance is so high, the load inductance is so high that your current is constant. Okay. This is, let us say, the supply voltage. Okay. This is the supply voltage. This is your angle alpha. And this is pi plus alpha. So in case of full converter, you are turning on T1, T2 here. Remember that we've assumed that the output current is constant. So when T1, T2 turn on, supply current is equal to the output current. When T3, T4 turn on, supply current becomes equal to the negative of the output current. Correct? Yes? I'm talking of the full
Yes, sir.
converter here, not the half converter. So if we draw the fundamental component of this current, this is the fundamental component. Correct? Hai
Yes, sir.
Sir.
This is your IS1. Okay. And this purple color, this is your IS. So this angle alpha is the same as phi for the full converter. Whereas if we go for the half converter, for the half converter or semi converter, we are turning on T1, T2 here. So your supply current is equal to the output current. Here freewheeling starts. freewheeling starts, so your supply current is 0. Here we are turning on T2, so supply current becomes equal to the negative of output current. And here again freewheeling starts. Is this clear?
Yes, sir.
Yes, sir.
So now if you plot the fundamental component, this is the fundamental component. Okay, the fundamental component does not start from here now. It starts from this angle. And what is this angle? This angle is alpha by 2. Okay. So your power factor for the half converter becomes IS1 by IS cos alpha by 2. So if you are operating it at 90 degrees, your power factor is not 0 anymore. It will be 0 only when the firing angle is 180 degrees. Okay. And for any value of firing angle, your power factor will be better as compared to what you get when you're operating with the full converter. Okay, is it clear now?
Sir, ratio of IS1 and IS will remain constant, sir.
No, it will not remain constant. It depends. Okay. IS1 by IS, the formula is different for half converter. I don't remember that formula, but that formula is different for half converter. Okay. Yes or no?
Okay, sir.
Yes, sir.
Formula is different. Okay. Means you can't assume that it is constant for full converter and half converter, but still you will find that the power factor will improve by a lot when you go for the semi converter or half converter. Okay. Without using anything extra. Plus, all this freewheeling improves your chances of continuous conduction. Is it not so? है कि नहीं है?
Yes, sir. Yes, sir.
Because if it is not freewheeling, then it is flowing against the supply. But when it is freewheeling, there is no opposition to the flow of current except for this armature resistance and the back EMF. But there is no supply voltage opposition to the flow of current. So your chances of continuous conduction are improved. Okay, when you go for the semi converter. And in case of the semi converter, semi converter, what is the expression for the average armature voltage? Continuous conduction. It is?
Say it is something in 1 plus cos alpha in terms of that.
Yes, it is Vm by pi into 1 plus cos alpha. Okay. So that is the advantage of using a semi converter. Is there any disadvantage of using a semi converter?
So it can work in only one quadrant, sir.
Yes, it will give operation only in one quadrant. You can get only motoring, you cannot get braking. Okay. Other advantages are there. Your cost is decreased because you have only 2 SCRs, the other 2 are diodes. You are getting better power factor, supply power factor, but the disadvantage is that you can operate only in one quadrant, single quadrant operation. Okay, if you want to further improve the power factor, or if you want to improve the power rating, then you have to go for 3-phase converters. Okay. Chalo, so I'll stop with the control rectifiers here. In the physical class,
Hello, sir.
Hmm.
Sir, book down, sir, attendance.